The topic of my talk is representation of Lestrygonian Nichols Algebra. This is a specific class of Nichols Algebra that Nicolas spoke yesterday, and I will review in more details who is this algebra, some properties, and we studied two things. We studied the finite dimensional simple modulus, and we studied the point modulus of these algebras. So in the first part, I remember the structure of the Nichols algebra Lestrygonian. In the second, we classify the finite dimensional simple modulus, and the last part, we classify the point modulus. About notation, K is an algebraic closed field of characteristic 0. The natural numbers, as usually, we denoted by n, not include the 0, and 0 include the 0. And we denote by IKT the elements of n0 between k and t, and IT the natural numbers between 1 and t. I start with the definition of Jeter-Drinfeld modulus. Nicolas told this topic yesterday, but I remember. Consider a Hopf algebra H, and what is a Jeter-Drinfeld module over H is a vector space V that has two structures, a structure of H modulo and a structure of H comodulo, and that satisfies a compatibility condition. Here I denote by ρ from V the structure of H comodulo, and we use this notation. And for coalgebra, we use the classic notation. Without sum. So this condition is the compatibility between the structure of modulo and comodulo. When H is a Hopf algebra with bijective antipody, we have that the category of Jeter-Drinfeld modulus is indeed a Brad tensor category. In this case, we have the following Brad between two objects. The Brad is given by this equation, this formula. Note that here V-1 are elements from H, and V0 are elements from V. So this is a map. Yeah, H3 means that delta composed. Particularly if you have an object here in this category, and you have automatically a Brad vector space, because C is from V tensor W, from W tensor V. When W is equal to V, we have a Brad vector space. So we assume that H is a Hopf algebra with antipoda bijective. In this case, we can associate for any object here a Hopf algebra in this category. This is not a usual Hopf algebra, it's a braided Hopf algebra. This algebra is the Nichols algebra of V. Nicolas told about this algebra yesterday. And this is a connected algebra generated in degree 1. Basically is a quotient of the tensor algebra by a specific ideal. There are equivalent definitions, but here I use the quantum symmetrizer. Okay. Consider V a braided vector space that is a block and a point. V1 is a block, is a vector space of dimension 2, and V2 is a point. This matrix, Nicolas told about this matrix yesterday also. This is the brad between the brad of V, the matrix of brad of V. But we consider a particular case. Here I put Q, and here I put Q minus 1. This means that the interaction between V1 and V2 is weak. It's a specific case of the general case. Okay. Remember that the G, the ghost, is the normalization of the number A, of the element of Ka. And in the case that ghost is a natural number, the Brad vector space associated to V is denoted by LQ1G. It's only notation. And we work with this algebra, the Nichols algebra of this particular vector space, Brad vector space. This algebra is generated by 3 elements, x1, x2, x3, but here we put more elements for technical questions, and satisfies the following relation. Here we have a quadratic relation. This is the relation of the Jordan plane. X1 and X3, Q commutes. This relation appears. These relations appears when you do the adjoint between X2 and Zn, and we have the Q commutation between X2 and zeta G, and this relation more. So we have 1, 2, 3, 4, 5 relations. In fact, more, because okay. This algebra is called Lestrygonian, or algebra of Lestrygon. The name Nicolas can explain better the origin of the name. some properties. This algebra is a domain, has PB double bases. Note that the M1, M2, and we have N0, N1, and G plus 1 more 2. Consequently, we have the Gelfand-Kirillov dimensional. Gelfand-Kirillov dimension is equal to 3 plus G. Is graded. The elements x1, x2, and x3, that is Z0, is 1, and the other one are given by this formula. And other thing is that the subalgebra generated by x1 and x2 is isomorphic to the Jordan plane because this relation. Okay, now I start the second part, that is to classify the finite dimensional simple modulus. I start with the quantum plane. Remember what is the quantum plane? The quantum plane is the associative algebra generated by X and Y with this relation, X and Y, Q commutes.
You have the Jordan algebra is a subalgebra of this algebra, and you can have also a map from this algebra to the Jordan algebra, sending all the other variables starting from x3 to 0. Is okay?
Yeah.
It's an algebra map.
Yeah.
Because I don't know exactly the relation.
Yeah. This is a map from the Jordan algebra.
You go to this algebra and then you go back and the composition is identical.
Yeah, exactly. Yeah. Okay. The quantum plane is the associative algebra generated by X and Y that satisfies this relation. When Q is 1, this is not the quantum plane, this is the algebra of polynomial in two variables. In this case, the finite dimensional simple models are all one-dimensional because X and Y commute. In this case, we can take a aging vector, a common aging vector is easy. When Q is not 1, we have the quantum plane. How is this finite dimensional simple models of the quantum plane? There are two classes. The classes of models of dimension 1, this and this, and has the classes of dimension n, on n is the order of Q. Something X act by X diagonally and Y act plus one more. We have this. And in the last one, to the first, here is N. Okay. So we have this result. This is classic, not new. The classification of finite dimensional simple models of the quantum plane is given by this. If dimension of V is 1, V is this or this. And if dimension of V is bigger than 1, the order of Q is n, and V is isomorphic to this model. So our first result is the following. The simple modulus here E-rep means the simple modulus of this algebra, the finite dimensional simple modulus. The finite dimensional simple modulus of the Lestrygonian Nichols algebra is this category is isomorphic to this category. Here we prove in 2 steps. Mm-hmm.
The second kind of model, that is it, no.
I'm sorry.
Is simple or in the composable?
This?
No,
Ah.
No. Yeah, this simple.
This?
Yeah.
Is simple.
It's simple.
Yeah, it's simple. This is simple.
Okay.
Mm-hmm. We prove this result in 2 steps. The first, we prove that we did ghost equal to 1.
What do you mean the categories, right?
I'm sorry?
What do you mean the categories, right? I mean, these are just sets, right?
I'm sorry?
I don't understand.
Huh?
E-rep is not a category, it's a set.
The set?
It's a set, yeah.
It is a set.
Okay. It's good category.
Ah, okay. Okay. First, we prove this. And the second, we prove G minus 1. So we reduce the general case to the case G equal to 1.
So the case in G equal to 1, I'm surprised because you have the x1 and x2 that have the relation of the Jordan plane, and then the x2 and x3 that commute, which is, this is why this quantum plane appears.
No. When we put
Can you say something about the proof of the first part?
the first part,
Do you just induce representations from the quantum
I'm
plane?
sorry?
Yeah, that's it. This is my question. Yeah. Is the induction of, because if you have a representation from the
So the key is that in the Jordan plane, there is an element that
nilpotent. Yeah.
in any finite-dimensional representation.
Yeah.
This is a lemma by Bagio.
Yeah.
Okay.
Using that, you reduce the representation theory of the Jordan plane to the representation theory of the quantum plane.
Yeah.
We did in a previous paper. And then by some going to the quotient, we reduce to that.
Because in this case, the element x1, x21, I'm sorry, x1 is nilpotent. So this part here.
Nilpotent here,
Chop.
but it's nilpotent in
Yeah.
every finite-dimensional
Infinite dimensional x1 is nilpotent.
In particular, if the representation is simple, then x1 is 0.
Yeah. Yeah. So the case G equal to 1 is simple. And this part is more hard.
At the beginning of your talk, you had this abelian group gamma.
Yeah,
But
this group you can think that gamma is this group, for instance. Is only to realize the breadth. You can think that gamma is Z to Z times Z. So this is the hard part. This. Okay. Now I speak about the last part. We start with a graded algebra connected and finitely generate in degree 1. Note that our algebra satisfies this condition because it's graded, is connected, and generated in degree 1 by 3 elements, x1, x2, and x3. What is a point modulo? A point modulo for A is a grade modulo V over A such that V is cycle and generated in degree 0. That means V is A V0. I think left point modulo. And V has Hilbert series 1 divided by 1 minus T. In other words, every component has dimension 1. Is the same. More notation, where a point of the projective space is denoted by A0, 2 points, A1, AN. Now I remember a classical result, the classification of point modules over the free associative algebra in n+1 ladders. The isomorphism class of point modules over A are in bijective correspondence with points of the infinite product Pn tensor Pn tensor, with the infinite sequence over Pn. How is this correspondence? If you take a point modulo over this algebra, we associate this element here in Pn because xi in general is an element of degree 1. When you act on Vj, we have an element of Vg+1. So these scalars you put here. But this is for all G, so we have a sequence, infinite sequence. In the column, you put the action of x0 in the first column. In the second column, you put the action of x1. In our case, we have this situation, x1 acts on Vj, we put Aj for the scalar, x2 Bj, and x3 Cj. So V is determined by this sequence when Pj is this, the action of x1, the action of x2, and the action of x3. So in this case, in our case, we have basically 3 possibilities. So x1 AVJ is AJ Vj+1, x2 it's easy to see that Aj is 0 if and only if Ej plus 1 is 0. It follows from the relations of the algebra. So this separate in two cases. This is the case more easy when Aj is not 0. That means that A0 is not 0. In this case, the elements that appears in the sequence are given by this. Pj is 1, B0 divided by A0 minus J divided by 2. And C, the action of X3 necessarily is 0 for all J. This is the more easy case. The other case is more complicated. When A0 is 0, that means all Aj is 0. And we separate this case in two subcases. The case of Bj is not 0 for all J, and the case that there is a J such that Bj is 0. So we have, in the case that Bj is not 0 for all J, we have that Pj is given by this, 0, 1, K minus J, C0, quotient by B0. And the other one, we have trivial. Pj is equals 0, 0, 1. Using these results, we have the parameterization of the point modulus over the Lestrygonian Nichols algebra, and are given by this set and this set. Because if you see here, we have an element that depends only on a constant, and here we have this, and here this. So the parameterization is given by these two sets aligned in the projective space, other line, and a point. Yeah. Thank you very much.
So why are they called Lestrygonian?
Nicholas can explain better, but it's of Greek mythology.
It comes from a poem by a Greek poet called Constantine Cavafis. The poem is about Ithaca. So you can Google it, Ithaca Cavafis.
And he mentions Coq algebras there.